they're in your notes, so I don't want you to turn it over and look at those four, right? It's already you turned it. Okay. What are the four? One is what? Two outcomes. There's one. That's a big one. That's why it's called binomial. There's two outcomes. That's one. What's independent? There's something independent in there, right? What's independent? Number of tests. Okay, you're using the wrong T word. Not tests. Tasks. No. Trials. There we go. So you had the right idea. So yeah, you're right. So the number of the trials have to be independent. There's another big one right there. Fixed number of trials is a big one. The two biggest ones probably are two outcomes, fixed number of trials. Each trial is independent. There's a fourth one. And this is the hardest one because you're going to have a hard time even thinking of examples where this isn't true. Probability doesn't change. Okay. Probability doesn't change. So why is that important? The probability doesn't change. Let's say I did this. If I say I'm going to roll a die 10 times, keep track of the number of fours that I get. Is that binomial? Fixed number of trials. Two outcomes. I either get a 4 or I don't. Does one roll affect the other? Does the probability change? No. Where it would not be binomial, still fixed, still independent, still two outcomes, is if I said I'm going to roll it 4 times. I'm going to roll with this dice the first time, this dice the second time, this dice the third time, and this dice the fourth time. Are there 4 trials? Are they independent? Is there a fixed number? Yes. There are 2 outcomes. Yes, on all of them, right? What are they not? Same probability. Okay, so that's the hardest one because most of the time you're doing the same thing over and over again. Of course the probability is going to be the same. But this gives you some idea how that could change for our formula. Okay, all right, so those were our four outcomes from last time, okay? Or 4 things that we had from last time. We looked at those. We looked at some notations, so we're all on the same page. We did an example, just actually working it out, and then we used the formula. We did that one with the formula, okay? We wrote down that formula. Why don't you write that down? Give Morgan a chance here to write that formula down. And then we'll go to the example where we're using that formula, okay? So let's try this one. Do we think we can do the formula from yesterday? Let's try it here. So try this one. Write down your NX, P, and Q. It says R. And you gotta put in your calculator. We get an answer? 0.0. See some nods, same thing. Now, let's flip back over to this one for a second. Okay, so flip back over two things. I want you to flip back over to this problem that we looked at yesterday. And then next, get out your formula sheet. Okay. Now, the first thing I want you to do in your formula sheet is go to chapter 4 on your formula sheet, which is the back of the first page. And you can see there's some of our formulas from our expected value and so forth. And about halfway down chapter 4, can you see binomial probability? And there is our formula. NCX PX Q to the n minus x. Everybody see that formula right there? Just to show you that that formula, everybody see where I'm at? I'm right here where my thumb is on chapter 4, is the formula we just used. Okay? However, one of the nice things about this formula sheet is we do not have to use that formula. So, flip back until you get to the first table of a whole bunch of numbers. Okay? And you'll notice at the top, table number 2, and it calls it the binomial distribution. Okay? So let's look at this problem. Okay? And talk about how you can use this table. The way your table is set up, you're going to go n is 8 in this problem. So down the left side, can you see where it says n is 8? Now, for 8, your x could be 0, 1, 2, 3, 4, 5, 6, 7, 8, right? All the way down. Does that make sense? Then at the top is your p. In this problem, our p was 0.7. So go over to 0.7, go to 8, 6, go down and over, and your answer right there is 296, which is what we got when we actually used the formula. Try that one in your chart. First off, here my n is 10. So what's the first thing you have to do in your chart? Flip to the other page. Your p is 0.6. And you get pretty nice. You'll notice this chart goes up to 15. It goes all the way up to 12, and then it skips from 12 to 15. So if you had a number bigger than that or outside of that, you'd have to formula. Also notice your p's at the top. What happens if I gave you a p of, let's say, 0.32? You have to go to the equation, right? So just understand when you do that, but a lot of times we can just use a chart. So let's look at a couple of these here. So using your table, suppose the probability of a certain treatment is 0.3. 12 randomly selected patients are given a treatment. Find the probability. So we're on 12. We're at 0.3. I'll also say this. People are tempted to draw lines on this chart to help them see. It makes it really confusing later when you draw arrows everywhere, because then when you go to stuff, so pencil or the cover of your calculator or something's really good to kind of help you go across rows extra sheet of paper or something like that, just to kind of keep track of stuff here. So if we are at 12, we want exactly 4. Our P is 0.3. I want you to look in your chart and write it down before anybody shouts out the answer to see if you get the right number. So try writing that down. N is 12, X is 4, P is 0.3. We have an answer? 0.23. Let's stop. Did anybody not see where we got that number? Look up, shake, no, didn't get it, or like just so eye contact. Are we okay? Are we understand where that number's coming from? We're good. All right. Try B. What is it? It's 0.000. Now, is this actually 0? No. So let me just show you here for a second. If we actually did this like with our formula, right? It would be 12, it was 0.3 to the 12, 0.7 to the 0, right? Would be our formula. So that would be 0.00000053. So is it 0.00000053 if we do it on the calculator? Our chart only goes to 3 decimal places. So based on 3 decimal places, the answer is 0. Do we need to go to the calculator to figure it out? No, we're just going to go to 0. And if you look, notice 12 is 0, 11 is 0, 10 is 0. We're up till 9 to its 0.001, right? What about none over here? That's pretty simple, just looking up a simple number, right? Where this gets a little more interesting is they get questions like D. What if at least 6? What would that mean? So at least 6 would mean the probability, and here's how I'm going to write it. At least 6, it's equal to 6 or more, right? So what would I add up to find at least 6? So now you want to take your chart and you combine it with the calculator. And so I'm going to write it up here so we can see. This would be at 6. It is 0.079, 0.029, 0.008 plus 0.001. All right, does everybody see where I'm at on the chart, going down the column? Now, if they weren't 0, I also would have to add 10, 11, 12, but I don't. And so we could add all those up. You got the calculator there. What is it? Now, it says in your notes, I'm going to add one more here to the bottom. if I said the probability of at least 2? How would you do the probability of at least 2? Same thing, yep, same thing, 12.3. Do the same thing, so what would you add up? So, somebody tell me what are the numbers that add up?
168.
0.168 plus
240.
240 plus
231.
231 plus
158.
158
079.
plus,
029.
oh, it's the rest from up there, okay, we're back to there, 0.008 plus 0.001, right? Is there an easier way to do that?
0.16. 1.2.
Subtract from what? So what are you thinking? You're on the right track, you're exactly right. Subtract this from 1? If this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, if I went and just did the probability
Not happening -1.
of 0 and 1, 0 and 1, wouldn't that be a lot easier than adding all of those up? Because what does, if you looked at this in every single one of these, each column for each n should add up to what? 1. So if I have to find something like this, instead of having to add up a whole bunch, if it's easier to add up the complement the other way, whatever that may be, and just subtract it from 1, that's much easier and quicker than adding up all of these numbers. Now, will it work to add up all the numbers? Yes. It's just more work, right? It's not necessarily hard work, it's just you got to do more arithmetic. All right. On your notes, one more before we move on to the next page here. Burglar system has 6 fail-safe components. The probability of each failing is 0.05. Find the probability for A, B, and C. I'm just going to let you go on those, and then we'll come back and share our answers. Just you read the question, use your chart. See if you can figure those out. All right, who wants to give me A? Because it was Craig.
0.002.
0.002. Good. Nod if you agree. Okay. Somebody else. B. 0.735. Second that. Nod with. Okay. And then C. 0.967. You got to add some up to get there, or subtract, or however you wanted to do it to help you get your ratings. Okay. Now, let's combine that chart with what we've already kind of done already. So, let's go to N is 4, P is 0.4, and think about adding the probabilities here to that. So from our chart, I go to 0.4, my probability at 0.4, 0.13. Is that what we got? Just ahead here. We get those numbers. Now, how are my numbers different than your numbers? I have an extra decimal place, right? So, these are from, you can get these charts, you know, more accurate, is you want those right there, okay? From what you did last week, what's the mean and standard deviation of that probability distribution? Do you remember how to do that on your calculator?
I'd rather do like the addition number, a little bit easier.
So the way we did this is, what are we going to do with these right here?
Multiply it.
Type, okay, you can multiply to find the mean, right? You're going to find the mean. Let's talk about the mean and standard deviation since we have the TI calculator here. You want to put this into L1, put all of your R's or X's into L1, and then put this into L2. And if you want to, we can think of this as X instead of R. So from that, does anybody find what the mean was? Do we remember, or do I need to do that on the calculator? What do you think? You tell me. So we go to stat. Zero, 1, 2, 3, 4, 0.1296, 0.3456, 0.3456, 1536, 0.0256, right? So you put them into L1, L2. You're going to go to stat, one variable stat. And remember, the important thing is you have to put L1, L2. If you didn't put L1, L2 here, it's not going to work right, okay? So you need this L2 right here for the frequency list, okay? Once you do that, you hit enter, and we get our X bar to be 1.6 and 0.9798 would be our standard deviation. So let me go back here. Sorry, the smartboard's not working right to write. I got to write from over here. We got 1.6 is our mean, and our standard deviation was 0.98. Remember, this mean is also what we talked about when we talked about expected value, right? So whatever this situation is, on average, you're going to get 1.6. Okay. Now, let's say we wanted to graph a binomial distribution. Can we see how we look at that graph? That's just like bars of our probability, right? It's a simple kind of bar graph histogram kind of thing. This is going to become really important in the next chapter. This idea that area represents probability. So if we look at this rectangle right here that I'm kind of shading in, this rectangle is
1 across, and it is 0.1296 high. So this area of this rectangle is just my probability. Area will equal probability. At this point, that means nothing. And you're like, what are you talking about? This doesn't really matter at all. It comes really important in the next chapter, so we want to kind of start talking about it now, okay? All right. So, if you have your formula sheet there, okay, you look at your notes. Your notes say the mean mu of a binomial distribution and the standard deviation sigma of a binomial distribution. Look in your formula sheet under chapter 4 and find what is the formula for the mean and standard deviation. What's the formula of the mean? What was of it? N times P. And your standard deviation is the square root of N PQ. So let's go back for a second. And we had looked at this one, right? Our N was 4. What was our P? So my mean is just N times P, which is 4 times 0.4, which this tells me the mean of this probability distribution is 1.6. That's the same thing we got when we actually typed it in our calculator. Here and got 1.6. So when you have these kind of probability distributions, you can type them into your calculator, or if you know it's binomial, it's just N times P, which makes sense. For example, if I told you 60% of students at Smithville drive to school every day. And I said, we go survey 100 students. How many would you expect to say that they drive? And how'd you get that? And it was how many students? 100. So didn't you just take 60% times 100? And 100 makes the math easy, right? But that's basically our formula. It's the number times the probability. That's the mean. That's the expected value. If I told you make the math harder so you can't do it in your head. If I take, 37% of students at Smithville have an Android phone and I go survey 48, how many would you expect to have an Android phone? Okay, we can't do that in our head. How many is it? Did you actually do it? I don't remember what I said. 37% times 48. And that's the expected value. It's just N times P. Right? That kind of makes sense. Okay. I don't know. What is it? What is the number? 18. Okay. You're going to get decimals when that kind of stuff, right? You're going to get your expected number is decimals. And is decimals okay? Sure, it doesn't have to be a real value, right? When we looked at some of those expected value problems for gambling, your expected value was, like negative 7.3 cents. Okay, you can't actually get 7.3 cents. So it doesn't matter, it's just the average, okay? All right. So we looked at that one, okay? So you can see here what this allows us to do is we now have a probability distribution where if we have a sharpshooter taking 8 shots, hits the target 70% of the time, what's our mean and our standard deviation? You're just gonna be plugging them in to our formula. And the last thing on your notes, we talked about this before. What does it mean for something to be unusual? Do you remember what the definition is? 0.05 or less than 5%. So when you're doing these, yes. Something that is unusual is less than 5. All right. Tomorrow we're going to do a Google Lab. And we got to go over our M&M data that you guys all put in. We got to do some work with that. So that's what we're going to work on tomorrow to get that done here before we go forward. We have one more section in chapter 4. So next week we'll look at that. We'll review and then take the test next week.